This is Statistics 243 at UC Berkeley for Wednesday, October 15th. Okay. So my goal for today is I'm going to finish off a little bit on the parallel unit, and what I want to do is just show you one other functionality in terms of parallelism in R, and use that as another example of some of these trade-offs in terms of what are some of the costs involved, different kinds of costs that are involved when you set up some parallel code. And then we'll switch over to the databases and big data sets unit after that. Okay, any questions from last time in terms of the parallelization stuff that we went over? So we saw for each, and I was just going to show you some of the parallel apply functionality. So much of this is in the parallel package, which is one of the core R packages. And there are a few different ways to do parallel applies. There's a par S apply, and there's a par L apply, and there's also an MCL apply. And I think it's just that they were written at different times by different people. So there are different ways to do these things, which is a little bit confusing. But the basic way that you use the various cluster apply type functions, this doesn't include the MCL apply, but the others, is you have to make this sort of management object, which is the return value of this make cluster function, and you have to tell how many cores do I want to use. So again, this is in a shared memory context, so you have all these cores that are accessing the same RAM. And so here I'm just going to pretend that I have 60 different iterations that I need to walk through, and then I'm going to do it in the context of an apply. And so I have some function that I want to use. I have to pass in this sort of cluster management object, and then I'm going to pass in the thing I'm doing the apply over. And then I'm going to pass in the function that I'm applying to the individual elements of that thing that I'm doing the apply to. And if we do this, again, I'm going to do a bunch of these examples on Radagast, so I'm just logging into the SCF server. So it looks like I forgot to load the package. Oh, okay. Yeah, hold on. Before I get to that, let me just point out that, again, I've got 4 different processes running here. Well, they were briefly. So again, this is functionality like we saw for each, where what's happening is in the master R session, it then starts up the additional processes it needs to do the parallel calculation. So where was the question? Sorry. Yeah.
What's the difference when we load a library or load a package, whether we say library or require?
I actually don't know. I think I looked this up at one point. Require is sort of more like if it's not already loaded, load it. But I think library basically behaves in the same way anyway. So yeah, it's a fair question, but I don't remember offhand. I use them sort of interchangeably, and I haven't come across a time where that causes a problem. So yeah, JR?
Somewhere that require does not tell you when there are errors, so it's recommended to use library instead.
Oh, okay. Huh.
Or something like that.
That's interesting. Okay, so we could play around and compare the time of doing this parallel S apply versus this S apply. I don't think I'm going to bother to spend time on that. Getting back to this idea of what are some of the sort of the bigger principles that come up when we're thinking about this. One of the things that one of the functions that sometimes you'll need to make use of in this context is this cluster export, and that's basically saying which objects that are in the workspace of my master process do I need to copy into the workspace for the worker processes. And so that has to do with managing how much memory you're going to use, because obviously if you have a very big object in your workspace, if each of the processes that then starts up has a new copy of that object, you're going to be using however many fold copy. You're going to be using that many times as much memory as you were using in your original calculation. And since this is all a shared memory environment on a single computer, that could very easily cause you to have issues with running out of memory. let's see. So the other thing I wanted to point out was this thing called that there's an argument to. So then another. This MCL apply uses a slightly different way of doing parallelism, but from sort of a user perspective, you can just treat it as the same. Again, I'm doing basically an L apply, but in a parallel way to the elements of an object. I'm applying this function to each of the elements, and here I have to specify how many cores I want directly in the function, as opposed to presetting it in that CL object that I had used for where I'd used the make cluster function. So just partly that was just to make you aware there are a few of these different functions. But the other thing that's interesting is to look at some of the arguments to MCL apply. And we'll see that there's this argument called mc.preschedule. And this basically has to do with the following, which I think we'll illustrate again what I was saying before about illustrating some of these trade-offs in how you do parallelism. Is if you think about, suppose I have this many tasks I need to do. Suppose there are 100 or 1,000 of these tasks. And let's say I have 4 processes that let's say I have 4 cores. Let's say I have 4 cores available to do the work. The MC preschedule has to do with one of 2 different ways of basically assigning tasks to my cores. One possibility is I could take however many tasks I have, divided by the number of cores in advance, so divide this into 4 pieces. Well, they should be equally divided, you'll have to imagine that. And I could take all of these tasks and assign them to core number 1. I could take all of these and assign them to core number 2, so on and so forth. And then basically I could just tell all the processes go, start doing your work. And then each of the cores could basically work through its set of tasks that have been assigned to it. So it's useful to sort of think about that compared to what's the alternative to doing, what would be the sort of natural alternative to doing that? What's the other way that I can think about getting all of these tasks done on the 4 cores? Yeah,
assign the first 4, and then when one core opens up, you just assign next.
Yeah. So you do sort of the more natural iteration through these tasks. So send out the first 4, sit around and wait until the first one that happens to finish comes back, and then send out the 5th one to that processor, and then just keep working your way through. So those are the sort of 2 different modes that MCL apply allows you to do, and I think that in this sort of thing would probably come up in other contexts. That those are 2 of the sort of main options. So what I wanted to do was sort of think about what are the trade-offs in those 2 modes of operating in terms of parallel processing. We've already sort of talked about some of the things that can come up last time, so I just want to sort of reiterate and see that in this context here. So what would be advantages of, or what would be the advantages of doing it the way that I've drawn out here?
I think this way you incur less communication.
Okay, so how do you want to say a little more about that?
Sure. So I kind of mentioned it last time. One problem that causes a lot of slowdown is when you have to have a lot of communication between your nodes or your cores or whatever.
And in this case, specifically between the master and the worker processes.
Right.
Yeah.
And so if you do it this way, you would have less communication, which would take up less time, so you have a lower runtime.
Yeah, so there's going to be less latency here because we only basically have to do 4 communications out and then 4 communications of the results back, because each processor is sort of managing its own work for the multiple tasks here. So the amount of latency or the amount of sort of messages you need to pass, that is this first mode, this sort of this in the preschedule is called preschedule equals true. So this is sort of a benefit for doing this pre-scheduling. Okay, other thoughts on advantages and disadvantages of doing it with this pre-scheduling way?
So if you do this pre-scheduling, if one core is very slow, it's kind of waste of. We can reduce this guy's task and assign to others.
Yeah, so that's what last time we called load balancing. So depending on what the calculation is, and depending on if something happens with one of the processors that for some reason it slows down, either there's something weird goes wrong with it, or it's just that you're playing Angry Birds on one of the cores and the other cores are free to do your work, right? What could happen is you send out, let's say there are 100 of these. You send out 25, try to make 25 of these. You send out 25 to the first core, 25 to the second core. These 25 take a lot longer on the first core than on the second core. And the result is your runtime is basically the maximum of the time it takes across each of the four. And if that is much different than the minimum or the average of those, then you're going to induce a cost from being poorly load balanced. So that's sort of a disadvantage for the pre-scheduling approach. Other thoughts here? I can think of one more thing. There might be things that I'm not thinking of, but I can think of one more. So when we were talking about communication, I said last time that basically there's a cost of any time you communicate a message to a worker. But there's also going to be a cost of how big is the information you need to pass to each of the workers, right? So how would that play out in this context?
For example, if the task is one task, it depends on another. So
Yeah, I mean, we're sort of assuming in all of this discussion, and it's a good thing to reiterate, that there isn't any communication between the workers, that it's all just between the master sending out the work to the workers and then the workers sending the results back. Any other thoughts? So what about actually passing big objects back and forth? This could sort of go a few different ways, I think, depending on the exact context. But if I suppose that I have some big chunk of data I need to communicate to the workers, is it going to be better to do it this way, or is it going to be better to send out 4 tasks, wait for one to return, send out the 5th one, send out the 6th one, send out the 7th one, etc.? Yeah. No. Well, I guess the question is, if we suppose each of the tasks involves the same big object, then which way are we better off doing this? Right. So less communication is better, and then is this going to involve less communication, or if we have to start up each individual process across the 100 tasks, is that going to be better? Right, so this way, if all of these tasks are indeed sharing the same big object, we just have to send it out 4 times, right? And then each of these tasks can use the same object, and so you only need to communicate that big object 4 times. If we're sending out the task, if we're starting up 100 different processes, we have to send out the big object 100 different times, each of them. So there's going to be that much more communication of the actual object that has to be, the object or objects that have to be passed out to the workers. On the other hand, I suppose there might be a context where each one of these is getting its own data. And if each one of them has its own unique data set that's getting passed out to it and there's no sharing, then maybe it doesn't matter, because what that means is I have to pass all 25 of these into the first one and all 25 of these into the second one, whereas if I pass them all one by one, I'm going to pass out this one to the first one, this one to the second one, this one to the third one, this one to the fourth one, and then I still have to pass all of them out, which just happens at a different time. And I guess you could also think about what would happen in terms of, depending on what exactly the problem is that you're working on, you might end up in a given one of these modes having more memory used at any specific point in time versus less memory used at any specific point in time, depending on how much data has had to be passed out to how many different workers. So you could, I'm sort of saying that vaguely here, but you might need to think about that as well, just again, back to this issue of not overwhelming the memory on the machine. Okay, any questions or comments there? So if we actually look at the pre-schedule argument in the help function for MCL apply, it more or less says sort of what we just discussed there. So here's the MC preschedule. It says first divided into at most as many jobs as there are cores. So the jobs are they're going to be the 4 different cores here. Each job possibly covering more than one value, so that's the 25 here. And then this is saying about short computations, variance and completion time, and load balancing things. So all of this is sort of getting at these same principles that we were discussing. And I think when it says the former is better for short computations, if you're having if each of your let's say instead of 100 there I had 100,000. If each of them is a very short calculation, and I have 100,000 messages get passed out to start the processes, that's going to potentially be the major part of the time that it takes. Whereas if I split up those 100,000 into 25,000, 25,000, 25,000, and 25,000, and then have each of the cores work through the 25,000, it's probably going to be a lot better to do it that way. Okay, so I think that's all I wanted to say about that. I'll mention a couple more things very briefly. If you have a very long vector and you want to do a parallel calculation on every element of the vector, you can actually do that with this pvec function. It turns out that this is not actually very effective unless two conditions are met. One is the vector is very long, because R usually does vectorized calculations fairly quickly. And the other is if the actual calculation you're doing on each element of the vector is fairly intensive. So if both of those, or some combination of sort of more of one and somewhat less of the other occurs, it might be helpful to parallelize your vector calculation. But otherwise, it's probably just going to be just as good to just do it serially on a single node or single core.
Just in the context, you need an order of magnitude for a big vector.
Yeah, I mean, some of it's just sort of experience and playing around, and that's what I end up doing is I just end up timing things. I would suspect that unless this, I think I played around with this some, and if this was like 1 million long or 10 million long, it was hard for me to find a case where it was useful to do this. So it had to be sort of longer than that. At some point, if the vector gets long enough, you start to deal with overwhelming the memory on your machine anyway. So that can also come into play here. But yeah, that's a good question. Good question, just to sort of have that in the back of our minds. And then there is a way to basically, instead of this sort of iterating through tasks that are often sort of the same task applied to a different portion of the data set or something along those lines, or maybe with a different set of random numbers, you can do sort of totally unrelated tasks in parallel, and you can basically call this MC parallel function and say, hey, on one process, go do this calculation, and maybe this is calling a function where the function is however many lines of code. In another process, go do this other calculation and then collect the results back. And I believe that what will happen when you call this is it will basically sit there and wait until each of the tasks that you've dispatched has finished and is able to return the results back. So again, this is a silly example, but an example of how you could take two things you need to do them at once, and then collect the results back, and then continue on with your calculation. Okay, so I think I'm done with Unit 7. I'm still trying to figure out, so I'm going to assign a very short problem set for today, due next week. Yeah, you're putting in quotes. I do think it won't take you that long. That'll be on computer arithmetic, and then next week I'll assign a problem set that covers the parallelization and the big data and the databases. And that one's probably going to be more extensive, and I'll have you guys doing some practicing with some of these parallel programming stuff. Okay, so let's switch over to, that got everybody talking? Let's switch over to the databases and big data unit. So this is sort of divided into three sections, three sort of core sections. I'm going to talk about SQL and databases. I'm going to talk about tools in R for reading in very large data sets and doing subsetting and things like that, sort of pre-processing and fitting models on very large data sets. And then I'm going to talk about Hadoop and distributed file systems and this tool called Spark for doing calculations in parallel in a distributed computing context. So that's sort of where we're going for probably the next 2.5, maybe 3 days. Oh, I guess I didn't open up the file yet. Okay, so I have a little bit of a sort of editorial comment here about big data, which is everybody's talking about big data. There's some of this I think is sort of just hype because it's sort of the new thing. Some of it is, I think, justified. But the thing I want to remind us all of when we're thinking about having very large data sets is they're sort of exciting because you have your hands on a lot of data and you could find interesting patterns and interesting associations, and maybe you can discover things that you wouldn't see amidst the noise in a smaller data set. But there are lots of reasons why we don't want to forget that we're still trying to think statistically about problems. And just because we have a large data set, it's not going to deal with the correlation is not causation problem. Right? There's nothing about this that's any different than any other observational data set that we have where we just happen to have the data that we have, if it is indeed an observational data set, which it usually is. And the other is usually these very large data sets are not collected in a representative way. They're just whatever data happens to be available because that's the data the company was collecting or whatever it was. I mean, maybe in some sense it might be a whole population instead of just a sample, but oftentimes it's not representative necessarily of whatever the larger population is that you're interested in answering questions about. And so nothing about having huge data sets gets around the issue that we could have biases from the fact because correlation is not causation and there are confounding variables involved, or that the sample we have might not be at all representative of the population that we're interested in. So those are just two sort of things to keep in mind about it. I don't know if this quote has everybody's already seen this like 7 times, because I've now started to see it a bunch of different times, but it's kind of fun, so I'll show it. So this is sort of what one person whose name I'm forgetting says. What's big data all about? It's kind of like teenage sex. Everybody's talking about it. We don't really know how to do it. Everybody else thinks everyone else is doing it, so everyone claims they're doing it. So if you're not really sure what you're doing with big data, don't be concerned, because it's like teenage sex. Nobody else really knows what they're doing either. All right, let's see. So the other comment I want to make here, sort of an editorial nature, is just because you're sort of confronted with a big data set, we already have some tools to deal with that. Like a lot of the tools that we saw in Unix for just processing through data files, we can use on pretty large data sets, and we can even do them in serial sometimes on quite large data sets, and they're still going to be reasonably quick. So don't give up just because, don't sort of think that you necessarily have to go find some sort of quote-unquote big data tool if you think you have a large data set. You may already have some tools that might be appropriate. And some of the things that we've already talked about. And the other thing is that I'm just highlighting here in the middle paragraph is don't just do simple things that are obvious, right? Like if you have some huge data set, but you're only interested in some of the columns of that data set, don't try and read the whole data set into R. Get rid of the columns you don't need using some tools in Unix, for example, and then read the data set into R. Or oftentimes, if you have a huge data set, you're going to be able to get a pretty exact answer from just subsampling the observations in the data set in a random fashion. So there's no reason you can't, particularly in initial stages when you're exploring the data, take your data set that has 100 million observations, pull out 1 million of them in a random fashion, and do the analysis on that. You're probably going to find the results are fairly similar to what you get with the larger data set. So there are oftentimes things that we can do that are pretty straightforward that don't require us to do anything in terms of using technology that we don't already know how to use. Okay, any questions before I dive into more sort of detailed issues? Maybe I'll ask a question of you guys. Are any of you sort of currently dealing with, and this might sort of specifically apply to the folks who are not in the statistics program, are any of you dealing with data sets that are, say, 10 gigabytes or 100 gigabytes or terabytes large? Okay, so you guys in nuclear engineering are. So how big are the data sets that you're working with?
50 plus gigabytes.
Okay, so that's sort of the scale of the problems that you're working on. Okay, that's useful to know. The data set that we're going to play around with some is this airline data set that's about 12 gigabytes, so a bit somewhat smaller than what you're talking about, but hopefully some of this will be appropriate. Yeah, this is roughly the same order of magnitude. And the idea is with this example data set I have is that hopefully some of what we're going to see would scale up to things that are larger than that as well. All right, so the first thing I want to talk about is sort of an old idea as opposed to a new idea, which is just the idea of databases and relational databases. So how many of you are familiar with SQL, or sort of more generally what a relational database is? Okay, so some of you, not everybody, and certainly not everybody confidently. So by confidence, I mean whether or not you're doing this. Okay, so I want to say a little bit about sort of what this idea of a relational database is, just so everybody has in the back of their in their mind. And I want to start it. I want to sort of motivate it by saying what sort of data set you might have that would not be in a relational database format, and why that might not be the best way to store it. So suppose I'm an educational administrator. I work in the central administrative office here. And I have some data set on all of the students at Berkeley and all the classes they're taking this semester, and who all the instructors of those classes are, and characteristics of the class and characteristics of the instructor. So I could think about having that data set, and I could just think about it as a big, flat, row-by-column data set of the sort we've been playing around with at various times. So what would that look like? Maybe this sort of unique field in that data set is it's a student database, and so it's the students. So we might have a field that's the student, and we'd have each of the students listed out, say, by name. And maybe we have their student ID and some other student level information. And now if I think about sort of what about the information of what classes they're taking, there's a multiplicity involved. So I would have, student A is taking 3 different classes, say. So I need to have fields to indicate what the 3 different classes are. So now I need things like class 1, class 2, class 3, right? So I've got to list that out. And now, now I need who's the instructor for class 1, who's the instructor for class 2, who's the instructor for class 3. So, there's an instructor for 1, an instructor for 2, an instructor for 3. And each of these classes maybe has a class size associated with it. So I've got a size 1, size, okay, you get the idea. My handwriting is getting worse and worse. And maybe the instructor has some information, so you have some idea of like the years of experience of the instructor or what their terminal degree was and things like that. Okay, so now this is supposed to be continuing the set of columns, so I have the instructor experience 1 and the instructor experience 2, and so on and so forth. Okay. So I've definitely gotten data sets like this, I've made data sets like this, you guys have probably worked with data sets like this. What's inefficient or what's sort of suboptimal about that structure?
You have a lot of students in the same class where they are not represented.
Yeah, so there's a ton of redundant information here. So let's say students A, B, and C are all in 243, sort of stat 243. Okay, and now we've got, instructor 1 is me. Okay, and we have the class size is 40 in all cases, and so on and so forth. Right? So there's a lot of redundancy. We could end up using up a lot of disk space, or if we try and read this into memory, a lot of memory by virtue of having all of this repetition. Other comments on this? What if I were just interested in the class information? And I just wanted to get that information and look at that information. What would I have to do? Yeah, so you need to go through and you somehow need to basically take this thing which is sort of has a multiplicity to it and pull out, you need to sort of pull out the unique parts of this data set to sort of construct a class data set that's just class specific without all the multiplicities. Anything else occurs to people? Yeah, Eugene?
In this databases, the big catch is the schema plays a big role in how you integrate things. So the thing very useful is if they come along table format. Yes, it's redundant, but at the same time, certain things are much faster to do that way than they are through a series of basically joint queries on the database.
Yeah, and we can talk about that. So yeah, so there might be some disadvantages to advantages to this compared to the other approach. Like if you're just going to go ahead and try and fit some model, eventually you might need it in this format, even with the multiplicities, because that's you need it in this sort of field observation format. So okay, fair point. The other thing that occurs to me is if I need to go in and make a modification here, suppose that I have to update this for next year. Well, and the instructors now all have 1 more year of experience, or there are new instructors I need to add. If I need to change anything in here, if I need to change, something about this particular instructor, about me, I need to go in and change it in a whole bunch of different places, because there's no unique place that says, what's the information about me? That really is just one value, but here it's got all this multiplicity involved in it. So another thing would be sort of thinking about as if you have to update this thing, it becomes much more messy to do that. So those are the things that occur to me. There might be, is there anything else that occurs to people? So, okay, so then we could think about how would we, sorry, I'm losing track of my papers here. We can think about how would we organize this in a way that sort of addresses some of these issues that we've just discussed here. And that gets at this idea of a relational database, which is basically to organize it such that we don't have these multiplicities that I was just talking about. So a standard way to do this for a data set that looks like this, spend all class walking back and forth, is, and this goes back to this idea of a schema, which was the word that Eugene used in terms of talking about how these databases are set up, is we would basically want to create a collection of tables where the tables are linked together by fields that basically allow us to connect them. So we might, for example, have a students table, and we could think that would have, say, name and student ID, and say what the classes are that they're taking. And then we could have a class table that would have, say, we need some sort of ID to identify each class, and then we would need, say, the instructor and the size of the class and whatever other information we had that was specific to classes, where there's just going to be one row for every individual class instead of that multiplicity. And you can continue on in this fashion. Maybe we have an instructor table, and that has the name and maybe the years of experience and whatever else, the terminal degree and anything else that we wanted to include in there. And now we have these, and one of the things that's sort of a little bit later in the notes is this idea of having a key field, which is basically the field that identifies the unique values in each of the tables. So in this case, maybe the names are unique, but maybe people have repeated names. So actually, maybe it's the student ID that's the unique that gives us the uniqueness of the table. So maybe this is the key field in this one, and then presumably the ID is a unique value in the class table, and maybe the name in the instructor table is unique, or maybe we have to worry about people sharing the same name amongst the instructors as well. And the idea of something called a foreign key is a key in one table that allows you to link to the primary key in the other table. So if, for example, in this case, if we were trying to merge together if we were trying to get back to that table over there, we would have to do a merge where we said, you know what, for every student, pull in information about the classes, and the way that we would link together the two tables is we'd say, well, we'd have to merge based on class 1 being equivalent to the ID variable in the class table, and similarly with class 2 and class 3, and then there'd have to be this linkage between the instructor and either the name or an ID here. So these foreign keys that sort of link to the primary keys are the things that allow you to link together the tables, and we could do a join of those tables that could get us back to this sort of that single flat table. Okay, so any questions about that big picture there? So when somebody says relational database, this is basically what they mean, that you have these different tables, and the different tables are related to each other by these linkages across the different fields. Okay. So there are a variety of different database management systems that allow you to work with these kinds of relational databases. So you'll hear terms like SQLite, MySQL, PostgreSQL, Oracle, Microsoft Access. All of these are different database management systems. Many of them allow you to make use of basically a single language for doing queries on the database. And that language is something called the structured query language. There are sort of different dialects of it that get employed in these different systems, but a lot of them use fairly similar syntax, and that is this SQL syntax. The other thing I'll point out here is that many of these database management systems are set up for sort of industrial scale applications where there's some big server on the back end, and you're the client, and you want to do some database query, and so you connect to the server. You send your query to the server. The server is sort of managing all the data on disk drives, and you connect and do the query and get the results back, and that's the sort of client-server model. For our purposes here, we're going to concentrate on something called SQLite, and basically the lite means that you can just have the database living on your hard drive locally, and you don't need to deal with all this client-server business, and you don't have to authenticate to some foreign server. All you have to do is just query your own database that you have control over. So that's sort of the idea here, just to keep things simple. And then the other thing I'll mention is that you don't have to, there are interfaces for, say, interfacing for doing queries in SQLite where you basically start up a little SQLite interactive session, and then you have to sort of know the syntax for using SQLite or these other things. But a lot of these you can actually use either R or Python as a front end and do the querying and sort of connect to the database and do the querying from either Python or R or some of these other languages. So the nice thing there is as long as we know Python or R, all we have to do is learn a little bit about making SQL queries, and we don't need to learn anything else about how what the syntax is of the particular program we're talking about. So that's what we're going to do is a little bit of an example of this. Any questions at this point? Okay, so we're going to work with an SQLite database that's available on the SCF machines, just for the sake of this illustration here. And what it is it's a database of all of the articles published in statistics journals over the last 100 years. So for some of us, this is a very exciting database. Some of the rest of you might not be so excited about this database. And so you can think about how would I think about coming up with a schema? How would I design a set of tables that would be able to hold the information about scientific journal articles in a way that makes sense in the way that this hopefully made sense as a set of related tables. So if we think about, we would sort of start, the way that you'd start to think about this is, okay, I have an individual article, and it has some information that's specific to that article, but the articles are also grouped into different journals, right? And then each of the articles has one or more authors, and each author may be an author on one or many different articles. So there's a lot of sort of cross-linking of this kind of information. So what would we need to do to what would be sort of a natural setup for breaking this up into a bunch of tables if we were going to design this? And then what we'll presumably see once we just sort of lay this out a little bit is that what we come up with should be essentially what is in this database. So what are some of the tables that I could use in this context of many authors, many journals, many articles, et cetera, et cetera? Kelly?
So you could break it up by journal. I would think that might be one of the.
Okay, so we might have a table that has the journals in it, and what would be our key, our field that has the unique information, our field that is unique, has a unique value for every row in this table? Yeah, either the name of the journal or maybe we'd assign the journal an ID number, but either way, one of the two. So maybe we'll have an ID number and we'll have the name of the journal. And then we could think about, there's probably some other journal-specific information that we might have here, the publisher or how long it's been around or whatever else. Okay. Other tables that we would have here? Okay, so the specific article. Okay, so what would be the fields in the article table? Okay, so the title of the article, the authors, well, we'd sort of need multiple ones for authors, right? So So we would need to sort of have author 1, author 2, that sort of thing. What else? Yeah, we need the journal so we can link back to the journal. So maybe we have, and usually, oftentimes, particularly in this example, this is going to be done with ID values instead of names. So in this case, we might have something like journal ID, and this would be the foreign key that would link to this primary key in the journal data table. What else do we have? What other tables? Authors. Okay, so we might have unique authors. So here we need, say, an ID for the author, same sort of thing as we've already talked about. We'd have a name for each author, and then we might have some, maybe we have an affiliation, an institution for each author, et cetera, et cetera. And we could sort of keep going in the same fashion. There might be a few other things that that we might have here. One other thing that this particular schema involves is something called authorships. I think it's called authorships. We'll see in a second. And the authorships idea is that it would be a unique entry for every time any author participated in an article. So basically, this would be this would have the author ID, and it would have, let's assume now there's an ID for this article. The article that would have the article ID as well. And this, in this case, I think in the case of the thing that we're going to see, I don't think there is an work here, so maybe I'll just have to see what it is. I think there might not be the author information in here.
Yeah, it's better to not have it in there, so you can have an arbitrary number.
Yeah, so okay, so you want to say a little bit more about how you're thinking about it, Chris?
It's just better to have a link between article and author as a separate joining table, like the authorships table, because then you can have 10 authors. You didn't have to create author 1 through 10 as columns in the article table. And you can also, you probably would add an order field to the authorships table as well, so you know what the order is.
The order of the authors in the...
Yeah.
Okay. Yeah, so then if we want to get, and then we're going to see this in a second, if we want to get from authors to article information, we basically need to go link from the authors to the authorships, and there we're going to link by this author ID. And then we're going to need to link to the article by linking the article ID foreign key here to the primary key here in the article database. And then that will allow us to sort of pull out what are the titles associated with a given author. And as you're sort of looking at this and realizing sort of there's some complication here, I guess that sort of maybe comes back to Eugene's point that maybe that there may be some disadvantages to this. I was sort of playing up what the advantages were, but it also, once you have to do all of this joining, it starts to seem a little bit more complicated, and you have to do all the steps of doing the joining before you then do the analysis.
Well, your schema is primarily based on what the usage for your database is. You can primarily search for authors, and you want authors to be linked to just for article titles, it's part of the base, and you want the article to be linked to the table.
Yeah, I mean, I guess I would agree with that in part, that if you're setting up the schema, then you want to set it up in a way that you can do the queries easily. But oftentimes databases are fairly, they're sort of meant to hold all this data, and different people might come to them with different kinds of questions. So they might not be totally designed.
You want your most popular.
Fair enough, okay. Okay, so let's see a little example of this, and I'm just going to show you some of the syntax where we can access this SQLite database using R. Okay, so first, again, there's this sort of front-end, back-end idea here that there's this function DB driver that is going to allow me to, in this case, I'm going to access I'm going to use the SQLite backend to access an SQLite database. But this could allow me to access other kinds of databases. Maybe I had something in MySQL format, and this could allow me to interact with that as well. So I'm going to set up this DRV object, which is another one of these connections that we've seen before. This idea of sort of setting up a connection to an outside source of information, and then being able to read and write to that connection. So here I'm setting up this connection to my particular database using this particular backend, which is encapsulated in this DRV object. And then I can go in and I can use some of the functions that are provided for interacting with the database. So I can say, well, what are the tables in this particular database, right? I want to know, do the tables correspond to what we're sort of dreaming up over there or not? And we can see indeed there's an articles table, an authors table, an authorships table. It looks like there's books and a journals table, because some of these things are going to be books as opposed to journals. I'm not sure what all of the rest of these mean. Some of this gets sort of into information details that we don't really need to concentrate on. And then we could do things like ask about, so this is getting information about the schema or sort of the metadata about the database. So I could say, well, what are the fields in the articles data table? And, well, okay, there's, where am I? I'm sorry. So in the articles, there's an ID, there's some sort of type thing, there's an ID for the title, there's the actual title, the sort of the words in the title, and this ID title again goes back to being able to link to some of the other tables, and then there's all the other sort of stuff you'd expect to have in information about article. What volume is it in? What page does it start on? Which page does it end on? Et cetera, et cetera. And so we could look at the same sort of information for authors or authorships. Looks like there's not very much information in the authors one. Okay, so then we can start to get into a little bit of doing a query. And let me just show you before I do that what some of these SQL queries sort of generally look like. And they're often of this sort of form, where you don't actually need to learn all that much syntax to be able to do a fairly wide variety of queries. So it often looks like this. Select these variables or fields from this particular table under this particular condition. So this is subsetting the columns or the fields. This is subsetting the rows or the observations. And sometimes we'll include to order the resulting output by some particular field. So often it takes that format, and then you can have these Boolean logic of sort of combining different conditions that we might have. So if we go ahead and do that in our example, here I'm going to do a very simple query where I don't do a lot of that sort of subsetting. I'm going to say take everything from the authorships table. I'm going to send this query to the database. I'm going to return it back as this sort of management object. And then I'm going to actually, if I explicitly want to take some of those results and get them back into R, I have to use this fetch command. So this says, from this query that I've set up, fetch the first 5 results. And so if I do that, I can go ahead and look and see what it looks like. And a bunch of these fields are these ID fields, so we have to do some more linkages to actually get things where we actually see the name of the author, the name of the title, and things like this, because these are just in terms of these identifying indices. But you could do a more interesting query that says, well, what if I wanted to start to just look for all of the papers written by this guy Leo Breiman, who was one of the prominent members of the statistics department. He died about 10 or 15 years ago. I guess I have to clear this result here. And what we'll see is, looks like there are 2 people with an ID that has a name like this. So what we'll see when we pick up next time is we're going to use this ID, or maybe both of these, to go try and pull in all of the articles that he's written and see what those titles and journals and whatnot are. So what we're going to try and do is do this sort of connection where we work our way from this to the authorships and then over to the articles and the journal information. So we'll do some queries that tie those things together, and then we'll see a few different ways of doing those kinds of queries. If anybody didn't get their problem set 3 returned from Jared, there are a few of them left here to pick up.